Okay, here we have a graph that I actually constructed fairly carefully to give us a y factor of 3. Now, I didn't construct it using compass and straight edge. I used my fingers so that this x value should double this one, and it seems like it comes fairly close. Maybe I went too far. This y value should triple this one, so I do this 1, 2, 3. It looks like I came fairly close. But from the results that I got, and from an honest attempt to do this by hand, I didn't get very good results. Now, what I was attempting to do was take this graph, construct its slope graph, and then estimate the y factor of the slope graph. Now, this assumes that the y factors, that the slope graph of a power function is a power function. So this assumes the slope graph is in fact a power function. Question marks there. Is that really so? Because we really haven't proven that. And this might then offers a counterexample. Okay, now as it turns out, it can be proved that the slope graph of a power function is a power function. It's kind of difficult to actually prove that using constructions. Still, constructions give us a much deeper insight into the relationship between the graph and the slope graph, and that insight can help us with later analysis that will indicate whether this is indeed the slope graph, is the slope function, let's say, is indeed a power function, and if so, how does the power relate to the power of the original, or how does the y factor relate, the y factor here relate to the y factor here? Okay, well, within that context, I constructed several slopes, just using the methods that I'm not going to explain again, as we explained in a very recent video. And then I constructed the corresponding slope graph. And I got something that looked like this, a slight upward concavity. It wasn't clear at this point whether it was actually going to even be an upward concavity. As a matter of fact, this point kind of started to indicate that it might be a downward concavity, but by the time we got here, it started looking a whole lot like an upward concavity. And then I just estimated the y factor. I have doubling values of x here, and it looks like the y factor is something around 2. By the time we get over here, I've got a little more than 2. So I indicated a y factor of maybe 2.1 or 2.2 with a question mark. Now, if we did this for graphs of y factor 3, 4, 5, 6, 7, 8, 7 halves, 9 halves, 11 halves, for a series of graphs, and we did this in class, trying to determine the y factor of the slope graph as a function of the y factor of the original, we would get a graph, okay, where we graph, we put the y factor for the f prime for the slope function on this axis, and the y factor for the original graph on this axis. I indicate that as y factor for f, our original function, and y factor for f prime, the function that corresponds to our slope graph. Now, I've actually drawn the curve as it probably is for the case, as it probably would be if we had completely accurate constructions. Now, completely accurate constructions are impossible. Okay, we can't construct any of these graphs down to the nearest atom, and even if we did, it still wouldn't be 100% accurate because atoms have size. Okay, there's no way to get an actual perfect curve and construct actual perfect tangent lines and so forth. We can be really careful and we can get pretty close. Now, this one isn't particularly close. For a y factor, for the f y factor 3 here, we got y factor 2.2 here. And as it turns out, that lies quite a ways above the ideal curve. The actual y factor would be this, whatever this happens to be. And I haven't drawn this to scale, haven't drawn it carefully. This curve isn't quite right. It can't be quite right. I just kind of slopped down a curve that had the right approximate shape. It's for you to do some of these constructions and see where you think the curve would be, and then compare that with where the curve actually is to get some idea of how well you were able to construct these things. And that's a good exercise. If this is the actual curve, if this was the actual curve, we would expect for careful construction to give us y values here, or vertical axis values that are much closer to the curve, maybe somewhere in this range. So if we have a point anywhere along this red segment, we think that we did a pretty good job with the construction. As we know, the y factor for a power function graph tells us exactly what the power ought to be. Okay, so we have the 2 to the p equals the y factor, and p is the log of the y factor divided by log of 2, those relationships. So we could transform this graph into this graph using the appropriate transformation from y factor to power, and we would get a graph that looked somewhat similar. There's some interesting properties of these graphs. One property of this graph, if you actually make it, looks like it might be leveling off. Does it have a horizontal asymptote? Okay. That means, is there a horizontal line that this graph won't go above, but will approach arbitrarily closely? Keep getting closer and closer, exceeding any limits you want to put on closeness, but never going above the line. Does this one have a horizontal asymptote? It might be out there a little further. Or does it perhaps have an asymptote that looks like this? Does it keep approaching some sloped line more and more closely as an asymptote? Interesting questions and good exercises to answer these questions. Okay, well, one takeaway from this, other than just these constructions and the reinforcement of the whole idea of construction, is that actual constructions have to be approximate. We can't do them exactly. They provide patterns and hints. They show us patterns, provide hints. One pattern might be that if you do this fairly carefully, this graph does appear to be concave down. This one appears to be concave down. Is that really the case? That's an apparent pattern. There might be an apparent pattern regarding an asymptote here or here. Maybe this one does appear to approach a horizontal asymptote. Maybe it's not a horizontal asymptote, but a slant asymptote. Maybe there's even a vertical asymptote if we go out far enough, and maybe there are no asymptotes. Okay, so those are all questions that we would like to be able to answer if we want to really understand everything there is to understand about this situation. We get insights. Okay, we don't get anything precise. We don't get anything exact from approximate constructions, but we can gain a great deal of insight and an understanding of the context that allows us to do further analysis and guides us in our further analysis. It can raise questions like the question of asymptotes. Now, we can then use numbers to calculate powers of different numbers and create more accurate graphs, a more accurate indication. We did this using Excel, for example, of how the slopes behave. Okay, and analysis of that numerical information, the numerical information we get on a trapezoidal approximation graph, gives us a better test of some of our ideas that we might get from geometric construction and gives us more detail. But just analyzing the numbers numbers all being approximate when you come down to it doesn't prove anything. Gives us a pretty good idea, doesn't prove anything. And then ultimately, we're going to have to resort on symbolic analysis. We usually require some kind of symbolic analysis to attain the level of proof. So we can see a lot and form a foundation through geometric construction. We can analyze numbers to give us a more precise idea of whether the patterns and so forth we see really emerge. But we need to go to symbolic analysis, do algebra, do calculus in that analysis in order to prove things. Turns out that there's an analysis we can do just based on algebra that does allow us to answer many of these questions.